Hi everybody, in this video we will be doing a review of forces. Let's start with free body diagrams. Free body diagrams are used to visualize the forces acting on an object. Let's start with this example, where we have a car that's accelerating to the right. How would you draw the free body diagram for this car? Well, you would start by drawing a point to represent the car. And now because the car's engine is pushing it forward, we would draw the thrust force. And we would also assume that there's some kinetic friction between the car's tires and the road. We know that the force of gravity will be pushing down on the car, and we have to draw the normal force, which represents the force of the surface pushing back up against the car. Now we were also told that the car is accelerating to the right. That means the net force acting on this car is directed to the right. So we draw the net force vector like this. Let's look at a tougher example. Here we have a box that's connected to a rope, and a person is pulling on that rope, but they're pulling on it at an angle. Now for this free body diagram, I'm going to draw my X and Y axis. And I do this just to make the direction of the force vectors a little bit more clear. So again, we start by drawing a point, which represents our box, and then the first force that I'll draw will be the tension force. So this is the tension in the rope. And notice, I draw this force at an angle. And because this vector is at an angle, we can break it up into an X and Y component. So we have Tx and Ty. And now how do we find Tx and Ty? Well, we can use vector addition and form a right angle triangle. Because we have a right angle triangle, you can use your SOHCAHTOA to solve for Tx and Ty. If you were to do that, you would find that Tx is equal to T cos theta and Ty is equal to T sine theta. And I urge you to try to do this on your own because it's important that you know how to find the components of a force vector that's at an angle. And now to finish off this free body diagram, we have the force of gravity pushing down on the object, we have the normal force, and there might be some kinetic friction between the box and the surface. And now let's end with one final example. This would be objects that are on an incline plane. And the reason I show you this example is because you need to draw your free body diagram a little differently. For this kind of question, you want to tilt your X and Y axis in the direction of the incline. And then you want to draw a point to represent your object. And the next thing you want to do is draw the force of gravity straight down. And then you can add the angle, which represents the angle of your incline, between the force of gravity vector and the y-axis. And now because the force of gravity vector is at an angle, we can break it up into an x and y component. So we have fgx and fgy. And if you were to use vector addition, adding fgy and fgx tip to tail to form this right angle triangle, you could use your SOHCAHTOA to find fgx and fgy. In this example, fgx is equal to mg sine theta and fgy is equal to mg cos theta. Feel free to check out my video teaching you how to answer forces questions when an object is on an inclined plane if you want more practice with this topic. And now to finish off our free body diagram, we have the normal force. And you will draw the normal force straight along the y-axis. And that's because the normal force always needs to be perpendicular to the surface. And with that, that's the end of our review on free body diagrams. Now, let's look at Fnet equations. Now remember, the net force is the sum of all the forces acting on the object. And we can describe the net force using this equation, which says that Fnet is equal to ma, where m is the mass of the object and a is the object's acceleration. The mass of the object has to be in kilograms, and the object's acceleration has to be in meters per second squared. And now remember, this equation describes Newton's second law, which says that the net force acting on an object is what causes it to accelerate. But also remember that the net force can equal 0. And that occurs when the object is not moving or the object is moving with a constant velocity. So if the object is accelerating, Fnet is equal to ma. But if the object is not moving, or the object's moving with a constant velocity, Fnet is equal to 0. And that brings us to Fnet equations. An Fnet equation is what you use to solve forces problems. You can make an Fnet x equation, which is the sum of all the forces acting along the x-axis, or an Fnet y equation, which is the sum of all the forces acting along the y-axis. Let's do an example. Imagine we have this person and they're pushing a box, and we are told that the box is accelerating to the right. And we want to know what is the net force acting on this box. Well, I always start by drawing a free body diagram. So I draw a point to represent the box, then I would draw the pushing force, the kinetic friction force, the force of gravity, and the normal force. And now I want to write my Fnet equations. And now because we have forces acting along both the x and the y-axis, I know I have to do an Fnet x and an Fnet y. Let's start with Fnet x. Fnet x is the sum of all the forces acting along the x-axis. So we have Fnet x is equal to the pushing force minus the kinetic friction. The pushing force is positive because it's a vector that's pointed to the right, and the friction force is negative because it's a vector that's pointed to the left. And now because I know the box is accelerating to the right, I can replace Fnet x with ma. Now let's look at our Fnet y equation. So this would be the sum of all the forces acting along the y-axis. We can see that Fnet y is equal to the normal force minus the force of gravity. The normal force is positive because it's a vector that's pointed up. The force of gravity is negative because it's a vector that's pointed down. And now in this case, the box is not moving up or down along the y-axis. So we can replace Fnet y with 0. And that's how you make Fnet equations. Now let's look at the various forces that we came across in the forces unit. Let's start with the force of gravity. We learned that the force of gravity can be found using this equation, which says that the force of gravity is equal to mg, where m is the mass of the object in kilograms, and g is the acceleration due to gravity. So that's 9.8 meters per second squared. Next, we were introduced to friction. And now there's two types of friction, kinetic friction and static friction. Kinetic friction is friction between an object and a surface when the object is moving. Static friction is friction between an object and a surface, but you would solve for static friction if the object is not moving. So kinetic friction can be solved using this equation, which says that the kinetic friction is equal to mu k times n, where mu k is the coefficient of kinetic friction, and n is the normal force. Static friction can be found using this equation, which says that the static friction is equal to mu s times n. Technically, we're solving for the maximum static friction. Watch my lesson on friction forces if you want to understand this in more detail. And in this equation, mu s is the coefficient of static friction, and n is the normal force. Next, we were introduced to the spring force. The spring force is the force applied by a spring that has been compressed or stretched. And we can solve for the spring force using this equation, which says that the force of a spring is equal to negative kx, where k is the spring constant in newtons per meter, and x is the spring's displacement from equilibrium. Check out my lesson on spring forces if you want to practice using this equation. And now we saw other forces as well, like the pushing force, the thrust force, tension, the normal force. And now there's more forces than this, but these are the main forces that you will come across in the forces unit. Now let's review Newton's third law. You may have heard Newton's third law stated as, every action has an equal and opposite reaction. Or you may have seen Newton's third law written as this: the force of A on B is equal to the negative of the force of B on A. And what this equation tells us is that if we have an object A and it applies a force to an object B, we can describe that as the force of A on B. But what Newton's third law tells us is that object B will also apply a force back on object A. And this would be the force of B on A. And this pair of forces have equal magnitude but are in the opposite direction. And that's Newton's third law. Now the next thing we looked at is what happens when two objects are connected and are moving together. So for example, if object A and object B are connected by a rope. And what we learned is that because these two objects are connected and because they're moving together, their accelerations are the same. And the reason I'm telling you this is because you will have to know this for Pulley questions. And these Pulley questions come up all the time in the forces unit. So for example, if we have these two objects A and B and they're connected to a pulley like this, if object B moves down, it's going to pull on object A. So object A is going to be accelerating to the right and object B is going to be accelerating down. And because they're connected by a rope and moving together, their accelerations are going to have the same magnitude, but they are going to be in opposite directions. Check out my lesson on Newton's third law if you want to keep practicing these Pulley questions. And the last thing I want to review when it comes to Pulley questions is the tension in the rope. So we have two types of Pulley questions that come up very often. We have the pulley where the two objects are hanging, and then we have the pulley where one object is on a table and the other object is hanging. And now looking at the first example, if we were to draw a free body diagram for object A and object B, we would see that both of them have the force of gravity pushing down, and they both have a tension force that's pulling up. And now what you have to recognize is the tension force acting on object A is the same as the tension force acting on object B. And that makes sense. They're connected by the same rope, so the tension is the same. Same goes for our second example. If we were to draw a free body diagram for object A and a free body diagram for object B, the tension force acting on object A is equal to the tension force acting on object B. And it's super important that you understand this because this is critical for problem solving when you're answering Pulley questions. And now the final topic I want to review is an object's weight. If you are asked to calculate an object's weight, you know that weight is equal to mg. M is the mass of the object and g is the acceleration due to gravity. But what you will most likely be asked to answer are elevator questions. And what we learned is that when you're dealing with an object that's in an elevator, and that elevator is accelerating up or down, the object's apparent weight, which can be represented by the normal force, can change. Let's look at what happens when an elevator is accelerating up. I'll start by drawing a free body diagram to represent the person in the elevator. We know the person will experience the force of gravity pushing down on them, and they will experience the normal force, which is the surface pushing back up against them. And remember, the normal force is your apparent weight. It's the weight that shows up on the scale when you go to weigh yourself. And now we know the elevator is accelerating up, so I will write Fnet is directed up. Now let's write an Fnet equation, which would be the sum of all the forces acting on this person. We know there would be the normal force minus the force of gravity. And because this elevator is accelerating, we can replace Fnet with ma, and we know the force of gravity is equal to mg, so we can do that replacement as well. And now I will rearrange this equation to isolate for the normal force. And look at this. The normal force is equal to mg, which is the person's actual weight, plus ma. And since the acceleration is positive, that means the normal force is going to be larger than the person's weight. And that's why the person feels heavier when they're in an elevator that's accelerating up. Now let's look at what happens when a person is in an elevator that's accelerating down. I will start by drawing a free body diagram, and if I were to write my Fnet equation, it would be the normal force minus the force of gravity. The person is accelerating down with the elevator, so I can replace Fnet with ma, and I can replace the force of gravity with mg. I'll rearrange and isolate for the normal force, and I can see that the normal force is equal to ma plus mg. But this time, the acceleration is negative. So the normal force, which is a person's apparent weight, would be smaller. And that's why a person feels lighter when they're in an elevator that's accelerating down. If you want more practice, check out my lesson on elevator questions. And that's the last topic that I wanted to review. If you want more practice for any of these topics, check out my lessons and questions that I've posted for the forces unit.